Hello and welcome to this Bio43 pre-lab video. Today we're going to look at a basic enzyme kinetics assay. The focus of this unit will be on the enzyme beta-galactosidase, or lactase. After you eat a bowl of ice cream, this enzyme breaks down the milk sugar lactose, a disaccharide, into glucose and galactose, which can be easily digested. Though that statement isn't exactly true for everyone. In humans, beta-galactosidase is encoded by the gene LCT, and most people stop expressing that enzyme in adulthood. Individuals who don't express this enzyme experience gastrointestinal distress after consuming dairy products. This condition, lactose intolerance, is common enough that beta-galactosidase is sold in pill form in most pharmacies. Given the importance of this enzyme, we want to develop a thorough understanding of how its function is impacted by other molecules. Let's design a sample experiment now. From past studies, I know that the product of an enzyme-catalyzed reaction can inhibit the enzyme. It can bind the active site and compete with the substrate. So let's hypothesize that galactose is a competitive inhibitor of beta-galactosidase. My null hypothesis is that galactose has no effect on beta-galactosidase. Pause here and think about how you could set up an experiment to test this. Well, the best way to know if something is an inhibitor, and what type of inhibitor it is to determine its effect on the kinetic parameters Km and Vmax. So for our control condition, we'll set up a series of reactions with different substrate concentrations and no galactose. We'll measure the V0 for each concentration and use that information to find Km and Vmax. For our experimental condition, we'll set up the same reactions but with galactose present and calculate the Km and Vmax there. If our hypothesis is correct, then, you know what? Why don't you tell me what the prediction should be in the pre-lab quiz, and I'll head to the lab. Here I've set out all the equipment we'll need for our assay. This is our buffer, potassium phosphate, O-nitrophenyl beta-galactoside, or ONPG, which will be our substrate for the reaction. More on that in a moment. It's wrapped in foil since it's a little light sensitive. Galactose, our hypothesized inhibitor, and our enzyme, beta-galactosidase. Then we have our cuvettes. We'll be running our reactions in these. Our spectrophotometer, which will measure the rates of the reactions. And micropipettes and tips for transferring liquids. Before we run our experiment, I want to talk about each of our reagents. First, the potassium phosphate. This is just our buffer. It ensures the pH stays close to 7. Galactose is our independent variable, which we hypothesize to be a competitive inhibitor. Again, beta-galactosidase, or lactase, is our enzyme. This is probably the only time you'll ever see an enzyme kept at room temperature rather than on ice. But this is a particularly stable enzyme, which is why you can buy it in tablets from your local pharmacy. In fact, this was prepared by dissolving an over-the-counter lactase pill in buffer and filtering out the filler material. I said ONPG is a substrate, but you just saw that beta-galactosidase catalyzes the hydrolysis of lactose to glucose and galactose. So shouldn't the substrate be lactose? Well, that would be ideal, but that would be a difficult reaction to monitor. There's no simple way to detect decrease in lactose or increase in glucose or galactose. But ONPG is similar enough to lactose that beta-galactosidase can bind it and catalyze its hydrolysis to O-nitrophenol and galactose. And while ONPG is colorless, O-nitrophenol is a yellow compound that absorbs light maximally at 420.7 nanometers. Here, I've set up two reactions. In the left cuvette, there is just ONPG and buffer. In the right cuvette, there's the same amount of ONPG, but I'm adding 30 units of beta-galactosidase. As the enzyme catalyzes the conversion of ONPG to O-nitrophenol and galactose, you can see the yellow color develop in the right cuvette. A spectrophotometer will provide a quantitative measure of how fast the yellow color develops. When we put a cuvette into the spectrophotometer, it shines a specific wavelength of light through the reaction, and a detector on the other side measures how much light made it through and how much was absorbed. The more O-nitrophenol is present, the higher the absorbance will be. Measuring the change in absorbance over time tells us the rate at which O-nitrophenol is accumulating, and thus the rate of the reaction. Here I have set up 7 cuvettes. They have ONPG at concentrations ranging from 1 to 13.4 millimolar, and enough extra buffer to bring the volume to 2.25 milliliters. I will add 100 microliters of beta-galactosidase to the first cuvette, quickly invert to mix, and place into the spectrophotometer. The spectrophotometer is connected to my computer and controlled by a program called LoggerPro. I'll tell it to start collecting data now. I've set it to measure the absorbance at about 420.7 nanometers, and you can see it tracking the change that's occurring over time now. As beta-galactosidase catalyzes the conversion of ONPG to O-nitrophenol and galactose, the absorbance increases. It will eventually start to level, but this first period of linear change provides us the initial rate, or V0. After 30 seconds to a minute, we can stop the measurement, perform a linear fit of the portion of the curve before it starts to level, and record the slope. That's the V0 for this substrate concentration. I'll repeat that process for the remaining 6 cuvettes and collect all the information in a table like this. The first column contains the different substrate concentrations, and the second column has the corresponding slopes, the V0s. However, these slopes are just changes in absorbance over time. Reaction rates should be changes in substrates or products over time. Thanks to Beer's law, we can make the necessary conversion. According to Beer's law, absorbance is equal to a constant called the extinction coefficient, times the concentration of the molecule, times the length of the solution the light passes through. The extinction coefficient of O-nitrophenol is 0.0045 per micromolar per centimeter, and the length of the cuvette is 1 centimeter. So if we divide the absorbance by 0.0045, we get the concentration of O-nitrophenol in micromolar. We can divide the values in the rate column that way, and now our V0s are changes in O-nitrophenol concentration. We can set up a scatter plot of V0 versus substrate concentration. This is our plot of choice when both the independent and dependent variables are continuous. Click away from the data, go to Insert, choose the basic scatter plot, go to Select Data, Add, ignore series name. For series X values, select the substrate concentrations. For series Y values, choose the V0s. OK, OK. Get rid of the title and add axis labels as you've done before. And this is our Michaelis-Menten plot. But as I said in the previous video, it's difficult to determine the equation that fits this curve. So let's make a reciprocal plot. Make a new column that's 1 over the substrate concentration, and another new column that's 1 over the V0. Note how the units have changed. Then make a new scatter plot, just as we did before, with these new columns as our X and Y series. This is our Lineweaver-Burk plot, and we want the line that fits this data. Add chart element, trend line. The default trend line is linear, which is what we want. More options lets us play with the design. It's nice to extend the line a bit so we can see where it crosses the y-axis. You could choose to extend it further to see where it crosses the x-axis as well. But what we really care about is the equation of this line. Display equation on chart, and record the slope and y-intercept. You can also get the slope with the equation equals slope open parentheses, select the y values, comma, select the x values, close parentheses. And the y-intercept is equals, intercept, open parentheses, select the y values, comma, select the x values, close parentheses. The Vmax is 1 divided by the y-intercept, and the Km is the slope multiplied by the Vmax. So we did it. We have Km and Vmax values for the enzyme without inhibitor present. There are some issues with getting Km and Vmax using the Lineweaver-Burke approach. Using the reciprocals can increase the effect of small measurement errors. Also, the analysis emphasizes the smaller substrate concentrations over larger ones. When you design your own experiment, you may want to use different substrate concentrations so that the reciprocals are more evenly spaced. Now, even though we set up 7 reactions to get this data, we have not performed 7 replicates. All 7 of these measurements were necessary to get 1 km and 1 Vmax value. So this is just one replicate of the control treatment. Repeat the whole process again with 7 more cuvettes, and we'll get another km and Vmax. A few more replicates, and we can calculate means and 95% confidence intervals for the values. A replicate of the experimental treatment will be nearly identical. Set up 7 more cuvettes with the same 7 concentrations of ONPG, but replace 150 microliters of buffer with 150 microliters of galactose. Add the same amount of beta-galactosidase you used in the control, get the slopes, and find Km and Vmax just like before. When an inhibitor is present, these are referred to as the apparent Km and Vmax. Do this a few times, and we can get means and 95% confidence intervals for the apparent Km and Vmax. Then it's just a matter of seeing if and how the Km and Vmax changed when galactose was added. In class this week, you'll analyze such data and decide whether or not it supports our hypothesis that galactose is a competitive inhibitor of beta-galactosidase. See you next time!